Okay, welcome everyone. Thank you very much for joining us today. So we are going to give you a few introductions to better give you an understanding of what we are expecting today, what are the outputs that we would like to gather during the day. But before that, please, I would like to give Peteris time to give a few introductory words. Thank you very much again for hosting us today for this workshop. And please, Peteris.
Thank you very much, Ludovic. Some of you have already heard this, but to give a little bit the background to what this workshop fits in and how it fits EU digital single market and blockchain policy. The Observatory and Forum is one of the actions we have coming out of the FinTech Action Plan, which was in the financial sector, but we've since expanded in blockchain, for instance, into all other sectors where blockchain is useful. It's linked to the European Blockchain Partnership, which is 30 European countries that are building a European blockchain services infrastructure. Some or many of you are involved with that, which will already be rolling out some use cases, public services, regulatory reporting, audit document certification already this year. We are also in preparation for the new European Commission, the new College of Commissioners, looking at legislative initiatives, possibly legal clarity that may be necessary in order to enable blockchain in a pro-innovation way, part of the European tech sovereignty push. You're aware probably of the excellent report of the Observatory and Forum on legal aspects of blockchain, including smart contracts, and we'll also have an invitation only, but you can all get invited if you're interested. Just talk to Lucas Repa here. A workshop of a legal study that we've commissioned, looking again at the possible initiatives that might be needed to enable blockchain. And then finally, this workshop, the lead up to our interaction with stakeholders, including the International Association of Trusted Blockchain Applications. They will be having, along with us and the Observatory and Forum, a global blockchain congress called Convergence, because it's about converging technologies, so cybersecurity, IoT, data, artificial intelligence, as well as blockchain. This is in Malaga, 11th to the 13th of November this year. Cybersecurity, among many other issues, ranging from the battle against climate change, to supply chains, to stable coins, including Libra, will all be discussed there. High-level speakers, the Finance Minister of Spain, the President of Latvia, Silvio Micali, the Turing Award winner, and many, many more. So we invite you all to come there, and now I'm happy to give the floor back to Ludovic to get into the meat of this seminar, during which I'll be happily listening myself and not speaking anymore. So thank you, Ludovic.
Thank you very much, Peteris. I have to emphasize on the fact that there are amazing speakers at Convergence, and I really encourage you to have a look at the website, see if there are sessions that you could be interested in, and I'm sure there are. So yeah, please have a look and join us. We would be very happy to have you there. So very quickly before we start to dive into the main topic of the day. So I just want to give you an overview of the objectives for today's workshop and a bit of context about what this workshop is about and what will be coming after that. So there are really two topics that we would like to cover during this workshop. The first one is really about the security of blockchain networks. We want to have a look at the security of blockchain networks, identify what are the main threats that are currently on hold of those networks, and see if there are anything that should be tackled, any priority that should be set, and any element that should be in the end, in our recommendations, in our report. The second aspect that we'll be covering during the day, so the first one will be covered mainly through presentations. We have 4 amazing presentations today that will be really covering extensively the topic on different aspects. So this should be covered with that aspect. And then on the second part of the day, mainly in the afternoon, we have a working session that will be mainly focusing at how blockchain can be used in order to increase the security of our systems, whether it be on the web, whether it be on any kind of solutions to today. And we want to have a look at the specific use cases, at the specific usage that are currently being created, leveraging blockchain technology. So very simple, nothing really fancy here today. But these are the two main aspects that we would like to cover today, and this is actually a really important topic. We have covered in the past with the Observatory and Forum many industry-based use cases or many focused use cases, and the few elements that we have already seen in the past are technical elements such as scalability aspects, interoperability aspects, and today we are really looking into security, which is one of the main components of those solutions. And so this is why this is important. And finally, to give you a bit of understanding of what is happening and why we are doing this workshop. So at the end of this workshop, we are going to publish with the Observatory and Forum a report, first report that will be basically just summarizing what has been said today, the main activities, the main ideas that have been shared. So of course, a good amount of the ideas that will be shared by speakers here in front of you today. However, the main ideas that we want to get are actually from you and from the exchanges that we are going to have during the day. So this is very participatory, and we really want to get inputs from you, the experts in the room, in order to build the content that we are going to show. And finally, the masterpiece that we are going to create after that, hopefully a masterpiece, and I'm sure it will be, thanks to Tom and all the team of the Observatory, will be a thematic report. And basically this thematic report is summarizing all the state of play around the topic and highlighting potential actions, potential recommendations and priorities for the different stakeholders, whether that be public institutions, whether that be standardization bodies, whether that be the private sector. All these different actors are being looked into, and the main goal of the day is really to feed the content of that report in the end, because this will be the most visible output and the most constructed output of the Observatory on this topic. So that's basically it. Maybe one last word on the agenda. So as you know already, there are a few presentations that are currently being prepared and that will be presented to you. Those presentations are mainly on the first topic that we have seen previously, and then the working session in the afternoon is really here to focus more on the use cases and the usage of blockchain in order to increase the level of security of the solutions. I hope this is clear. I'm going to stop for 1 second to see if there are any questions before we start really to jump into the actual content of the day. All clear? Excellent. So please, let's start directly into it. I would like to welcome our first speaker, Stefan. Please come here on stage with us for the first presentation. Please, a round of applause for Stefan.
Okay, so good morning everyone. I represent the cybersecurity company, and we focus on blockchain security. And myself, I'm from a distributed systems background and then moved into cybersecurity, but these days I describe myself as a smart contract auditor. But anyway, this talk is about blockchain security and the problems that are there in current blockchain security, in particular in getting digital assets to be secure on the blockchain. So there's a question here, are blockchains secure? We ask this a lot by our clients, and I mean, what do you think? Are blockchains secure? I mean, it's obviously, if I give a talk about it, there must be something to it, right? So, well, my answer is yes. Usually they are secure in terms of the cryptographic protocols, right? So the math below is sound. The cryptography has not been broken yet, and that generally works. But the digital assets that are represented on the blockchain, they are usually not secure, right? They're not secure for a number of reasons, but it's obviously a problem, because the killer use case of the blockchain is to represent digital assets, right? Whenever we use a blockchain, there's usually some value involved, whether that be a cryptocurrency, a token, a share of a company, even a certificate, intellectual property. There's usually some value being moved around on the blockchain. Right? So that's what we call digital assets in this case, and they are not secure. And just to back this up, here are some numbers from two reports that I saw in 2018. And one stated that in 2018, $1.7 billion in digital assets were stolen or lost on the blockchain. Now that's obviously just a number from a report. Depending on which report you read, you get a different number. But we can all agree it's a lot, right? If it's 1 billion or 2 billion, it doesn't really matter. And another interesting fact that I read was that 2 groups have been identified to be responsible for most incidents. Now again, we don't know if that's true, right? But it doesn't matter if it's 2 groups or 5 groups. The important news here is that it's become a business model, and there are people that dedicate themselves to steal digital assets. And that's obviously worrying, that it's profitable for them. So what are the security concerns on blockchains? And surprisingly, most of these are not even related to actual blockchain technology, right? The only one that I would classify as pure blockchain related is the use of smart contracts. Whenever we use digital assets, there is some sort of smart contract involved. But in most cases, there are blockchains that don't support smart contracts, but they'll have some form of scripting, and usually complex blockchain applications have some smart contract in there somewhere. And smart contracts are extremely difficult to get right and secure, which we'll talk about in a bit. But most of the code in a blockchain application is actually off-chain code. That's traditional code, databases, APIs, user interfaces, and they share the same problems as traditional software. So there's nothing new to this, but maybe 90% of blockchain applications is actually code that is run off-chain. And the same goes for infrastructure, right? A blockchain node needs to run on an operating system, it needs to run on a network, and there might be vulnerabilities there. And finally, the worst for cybersecurity is human intervention, right? So every cybersecurity analyst will tell you that whenever there's a human in the system, that's sort of a worst case scenario, because for a number of reasons, but humans are unpredictable, and they use systems in a way that we don't imagine. So usually they're humans interacting with off-chain code that runs on traditional infrastructure, and then in the end there's a smart contract involved. And all these can have vulnerabilities. So let's look at these. So smart contract security I don't want to talk too much about, because there will be talk about this afterwards. But generally smart contract has 3 main properties which are essential to make them work, but they also introduce a big security problem. Now, first of all, smart contracts are publicly readable, right? So everyone can read the smart contract and what it does. And they usually hold value. I can write a smart contract to write the name of my wife onto the blockchain forever, but that's not of interest to anyone, right? So the really interesting smart contracts generally hold value. And they're mutable, which means they cannot be changed, which is obviously important, because if you consider the contract, you wouldn't want the clauses to be changed. But it also means you cannot fix any vulnerability or bugs you encounter in them. Once a smart contract is deployed, it is there. So you cannot change it. You can just redeploy a new version, which is not always possible. And that obviously converts them into very interesting targets. So for cyber criminals, a smart contract is quite interesting for these 3 properties. So just a quick list of some security incidents, and I've chosen these because of the impact they had and the interest. There are many more. But in 2017, we became aware of all this with the DAO attack, which you've probably heard about. I'll talk a bit more about it in a minute. But basically, $70 million were lost, temporarily at least, there. And then at the end of 2017, Parity had a big incident when their multi-signature contract, which was open source and used by a lot of startups, had an important library blocked, and that had the result that $300 million were frozen on the blockchain forever. And I won't go into detail of this, but that's obviously important in large numbers. And they're interesting because the DAO attack, we're still suffering the consequences. And the parity, it's interesting because it's one of the main companies in the blockchain, in the Ethereum ecosystem. And obviously people trusted their code. They thought parity should get it right. And in 2019, there's an interesting case when the Ethereum Constantinople update had to be postponed because it would have made smart contracts already deployed insecure. And we'll have a similar situation in 2020. And I'll talk about a bit in one of the case studies afterwards. But it's obviously a worry if the underlying protocol changes and immutable smart contracts suddenly become insecure or stop working. So these are just some numbers from just the statistics I had from last year. So I audited 22 fairly large projects, anything from investment funds to tokens and prediction markets. But these are the issues I encountered. And there are 16 critical issues, 16 major and 36 minor issues. And obviously that's not linearly distributed. There are good projects and there are bad projects. But the interesting fact here is that in none of the projects it could be considered flawless. So this just shows that even big projects get it wrong, and it's incredibly difficult to get smart contracts right the first time around. So.
Can I just ask you one thing about the previous slide? In this case, for example, the 16, 16, and 36, is it possible that, for example, a lot of those issues would appear in one or two or three projects, for example?
I'm sorry, just say, can you please introduce yourself when
Yeah, sure.
and speak in the microphone, please?
Yes, my name is Mikael and I work for CRAB. My question is, when I look at this, whether the 16, 16 and 36, so all those problems that you identified, were present, for example, like in 3 or 4 projects, or should we understand that most of the 22 projects were actually problematic? I understand that they were flawless,
Yeah.
were 0, but like, just to kind of get an understanding, because I mean, if there is 16 projects out of 22, it makes a lot of problematic projects.
Yeah, without having the actual numbers in my head, my feeling is from looking at smart contracts on a daily basis, that most smart contracts have some issues. And obviously critical and major issues, these 16 were probably in about half of these projects. But minor issues are still small mistakes that don't follow best practice. And that's the type of thing that would have made smart contracts insecure if the Constantinople update had gone ahead as planned. Right? So it is a worrying statistic in a way. But that's all I want to say about smart contracts, really. Almost all I want to say about smart contracts, because we'll talk about auditing in another talk afterwards. But in terms of off-chain code, now that's databases, websites, key management solutions, APIs, user interfaces, and that it is really traditional software. But they make up 80% or 90% of blockchain applications, and people often forget about security in these, because if you are interacting with smart contracts and value on the blockchain, this is a very likely attack scenario to get in that way. So common incidents here include unsecure authentication, traditional authentication tokens being passed around wrongly. Cryptography is very misunderstood. A lot of people don't know how to use cryptography and don't know how to manage and generate keys securely. Exposing keys is quite common, accidentally. And then there's traditional software vulnerabilities, and particular interesting are backdoors. That unhappy employee that leaves a backdoor in the software. That's a common incident. So infrastructure is very similar to off-chain code. Blockchain software needs to run on nodes, on computers. They have operating systems that have vulnerabilities. Network security is important. There might be open APIs that shouldn't be open. Permissions might be set incorrectly, and that's also an attack scenario. So incidents here, as already mentioned, the node software itself that connects you to the blockchain might be faulty, might have a vulnerability. Security at the operating system level, at the network level, and the type of things we see there are denial of service attacks to nodes, Eclipse attacks. Eclipse attack means isolating a node so that it only sees its copy of the blockchain, which might be out of sync. And quite common is to leave APIs open. An example of this is on the Theorem nodes, the JSON RPC, which is one of the APIs often used. That port is sometimes forgotten and is open there. It's insecurity. But yeah, as I said before, the worst in terms of cybersecurity are humans. And it's really for a number of reasons, but humans are generally lazy. They use inconvenient or easy to remember passwords and that sort of thing. They take other shortcuts. And they behave irrationally in the sense that we don't know how they will behave. They behave unexpectedly, so we cannot predetermine the human behavior of a user. And that leads to a trade-off, which is very difficult to resolve in blockchain applications, and that's the user experience versus security. You can make a system very secure, but then it's unusable. And that's something that has to be configured with a lot of care. But in general, the human is the weakest link in the chain. And common incidents here, as I said, security shortcuts. Social engineering is a very big problem. Phishing attacks and social engineering become very sophisticated. No one is safe really there. It's there's dedicated teams looking at how people behave and how they act on social networks, and earn a lot of information on them to make them believe they're someone else. I freely admit that I've been talking to clients through Telegram for 20 minutes, and I was actually speaking to an imposter. But these people that just learned so much about the project and knew exactly what we are usually talking about, that it was very difficult to realize that I was not talking to the actual person, and that's a very big problem. Information is leaked easily, usually by insiders. The insider attack is probably the most common attack in these exchange hacks that we always read about, like someone suddenly dying and then appearing in India and spending their Bitcoin. So that happens frequently. And yeah, so these are the 4 areas I identified there on one of the early slides. And I did say that the protocol is secure in terms of cryptography at the beginning. And obviously that's an exaggeration. The protocols work because the cryptography works, but there's still protocol security worries and attacks that are possible. And just list a few here. So that's the famous 51% attack, which basically means someone gets hold of more than 50% of the computational power in a proof of work blockchain, and reorganizes the chain. And that's happened a few times now, and it's relatively easy because the hash power can now be rented on an hourly basis, and you can actually rent it for a particular algorithm, and it's very easy to do. And it's actually profitable in some cases. There's something called selfish mining, which is when a miner increases his chances of getting block reports by delaying publishing the blocks they find and already starting on the next one. That's been observed a few times. In proof of stake, we have something called the long-range attack, which is fairly similar to 51% attack, basically rewriting the blockchain. And another thing related with proof of stake is poor randomness. Because if you think about how proof of work works, it's not just a consensus mechanism, it's really a giant, very expensive random number generator. Right? It chooses a block producer randomly by weighting it with computational power. Right? So there's a random process, a puzzle, a lottery, and there's a weight that makes it more likely for me to win this lottery if I have a lot of computational power. But obviously in proof of stake, that randomness is lost because we don't have this lottery system anymore. And it's very difficult in a deterministic system such as blockchain to create true randomness. And that's what the Ethereum 2.0 people are finding out now. The very difficult subject there is how to create the randomness required to be truly secure. And in delegated proof of stake, we can have delegated collusion or validated collusion. And I won't go into too much details of these, but there are obviously protocol security issues. So having looked at what the issues are, I've selected 3 case studies here, and I've chosen them on the basis on the impact they had on the blockchain community, and also I've chosen only incidents that are really related to blockchain security, right? So I've not chosen exchange hacks where there was someone stole someone's private keys through phishing, because that's traditional cybersecurity. It's not. It's very important, but not too blockchain related. So the DAO, I'm sure you've all heard of this famous incident in 2016. If not, I'll encourage you to read it up. I've chosen it here because of the effect it still has on what we do. And in particular, the attack here was a reentrancy. And that's the only piece of code I put up there. I don't know how many programmers are in the audience, but it's not important to understand it. Basically, a reentrancy attack is a smart contract attack where there's usually assumption that when you interact with an address, it is a person or an external account. But it doesn't have to be, it can be a smart contract. So reentrancy attack happens when you send value or you make an external call to an address that is a smart contract. And that smart contract can actually execute code when it receives a payment or a call, an external call. And in this case here, really we send some money to an address and afterwards we set the balance. But what this contract can actually do when it receives this payment, it executes code that calls back to this function again. And the balance is not 0 yet, so someone can actually withdraw more money than they hold. And that's, if you don't fully understand the code or the technical detail, it doesn't matter. It's just one of these things that are unique to smart contracts. And they're still giving us problems today. And in the DAO attack, the DAO itself was sort of a crowdsourced fund organized in smart contracts. It was decentralized autonomous organization, which is obviously we're still trying to do, organizations run by smart contracts. And the interesting fact here is there were 12.7 million ether located at a single smart contract address, which was much more than the team behind the project actually expected. And that's always worrying when there's so much money in a single place. But anyway, in June 2016 there was a re-entrancy vulnerability in the contract. Someone exploited it and managed to create a child DAO, which basically meant that he managed to get some money off other people, and that was locked away for 28 days. Right? So during these 28 days, people realized what had happened and tried to solve it, and they had 28 days to recover these funds. And the fallout was that some people decided they wanted to rewrite history in the blockchain, break the laws of immutability, and others were against this, and Ethereum essentially forked into 2 different projects, Ethereum and Ethereum Classic. And obviously the DAO as a company collapsed, and the temporary Ether price crash was there, but the really interesting fact from a cybersecurity point of view for me is that it still keeps happening. We still have re-entrancy incidents almost 4 years afterwards. And this chart here is how we deal with re-entrancy from a best practice point of view. And in 2016, when this happens, we were told to use these 2 functions, transfer and send, instead of call value. Now the difference just is here that if you use transfer or send, the recipient cannot execute a lot of code because he will run out of money, out of gas. Right? So that's all you have to understand here. It basically means that there's a limit on the money forwarded to execute a transaction. So he cannot perform the attack because he runs out of money. And then in 2019, we had the Constantinople Protocol update, and if that had gone ahead as planned, the gas prices would have changed. And this meant that some projects that had already deployed their smart contracts would have them not secure anymore, because the money sent forward to the recipient was actually enough to perform the attack in some cases. So then we changed, including ourselves as a company, we changed the advice we give to smart contract programmers, and we told them to avoid state changes after external calls. If you're not a programmer, it doesn't matter. Important messages here, we changed the best practice guideline. And now, at the beginning of 2020, there will be another update in the Ethereum protocol. And this time it will happen again. Some smart contracts will stop working. They will not become insecure, but they will run out of funds. Right? So it means that they cannot be executed anymore. And the interesting thing here is we go back to pre-2016. We tell people now, use core value. Right? So in 4 years, what I want to say here, we've changed the practice guidelines several times. We're now back to where we started. And we still don't know how to do this properly. So it's a very immature ecosystem, and we're still trying to work this out. Now, obviously, that directly clashes with immutability, right? So there's a big dilemma between protocol updates, immutability, and security, right? So smart contracts are expected to be there forever. A company, a business that wants to deploy a smart contract now has to assume it will be there forever, or at least have a very long lifetime. But the actual protocol change coming up might mean that's not true. So that obviously stops a lot of people from doing complex things in smart contracts. The second case study, I'll go through that very quickly, is front running. It's blockchain specific, and basically it means that everything on the blockchain is public, right? Even non-confirmed transactions. So if we're sending transactions to a network, either Bitcoin network or Ethereum, they go to something called the mempool, and miners or validators just select them one by one and include them in blocks. But meanwhile they're there, everyone can see the intent and purpose of this transaction. And that's quite unusual in software. Right? And they might be there for hours even if the network is fairly busy. And a front-running attack really just means overtaking a transaction. So you have a transaction of interest and you want to get there before. So you submit another transaction with a higher gas price. So you're paying a higher transaction fee just to get it prioritized, and it will overtake the original transaction. And that can be used in trading, obviously. It's used quite frequently in trading. There's actually a vulnerability in the ERC20 standard. So you've probably all heard of ERC20 tokens, which are used to represent all types of programmable tokens. And there's actually a vulnerability in there that means that someone can spend more money than he's approved to spend. And that's if you use it in the original specification of the actual standard. But there's ways around this, obviously. And another example was in Banker. They had a security incident with the early smart contracts based on front running. But it's fairly common, and it's very blockchain specific. So, in the third case study, I just listed some attacks that have actually happened on blockchains at the protocol level. And 51% attacks in particular have become fairly popular recently. In 2018 and 19, we saw quite a few high-profile cases of smaller blockchains getting attacked, including Ethereum Classic, Verge and Bitcoin Gold. Now, that's a direct result of fragmentation. So if if you split up blockchains and people have the Bitcoin, Bitcoin Cash, Bitcoin Gold, Bitcoin SV, whatever, without getting into the political details behind this, the problem from a security perspective there is that you end up with a lot of smaller blockchains with a lot less computational power behind, and they are easier to attack, which is what has happened to these blockchains. The Verge attack was also interesting. Verge was a blockchain that tried to be too clever, or is a blockchain that, in my opinion, tries to be too clever. They have 3 different mining algorithms and a very flexible timestamp system. And there was an attack where the attacker actually managed to lower the difficulty by manipulating the timestamp. And having 3 different algorithms meant that each of them had a lower difficulty anyway, so it was much easier to perform a 51% attack. So being too clever and doing too many things in a protocol is not a good idea. And then the last one here is the Lisk blockchain, also fairly popular project, or at least it was. I don't know what they're doing now, but it's been a bit more quiet recently. But they have a vulnerability in their protocol which basically related to not understanding cryptography. Well, I understand it now, but I didn't at the time. And what happened there is that the addresses that are generated are not linked to the accounts at creation time. So a public key, public key is not mapped to an account address directly. You have to claim it afterwards through making the first transfer or doing something with this address. And that lowers the difficulty of a brute force attack, and it actually meant it became profitable to just discover a matching key for a certain address through brute force. Yeah. Just to finish off, after these case studies, just some trade-offs that have to be looked at when designing a blockchain application. So security, there's always trade-offs involved, right? And the first one we've already mentioned, usability versus security. On the one side, we have hardware wallets, complicated mnemonics, long numbers, long keys, or keys locked, written down on a piece of paper and locked in a safety deposit box. But that's not very usable, right? So it's not user-friendly at all. To make it easy for people to use and make it efficient, security has to be relaxed somehow. And that's a very difficult trade-off to get right. Then at the protocol level, there's a trade-off that has been known about for at least 30 years in distributed systems, and it's to do with consistency and availability. And basically the CAP theorem, as it's called, means that if you have a system that can partition, right, a blockchain, it's a peer-to-peer network where nodes can get disconnected, reconnect, there might be a cut in the network and some nodes are isolated. If you have such a system, you have to choose between consistency and availability, which is really obvious, because if a node is disconnected, it cannot be consistent with the rest of the system, right? So in Bitcoin, we greatly favor availability, right? You can have a fork in the blockchain, temporary fork, and a transaction can be undone after 3 or 4 blocks still. And that's why we are generally told to wait 6 blocks or about an hour before we consider a Bitcoin payment to be secure or confirmed, right? It's because we favor availability. Other blockchains like Cosmos favor consistency. But what that means is they always want a very consistent state in the network, and it means that if nodes become separate or there's a partition in the network, they have to stop. So they're actually freezing the system and don't accept any more transactions. And that's something you have to consider when designing a blockchain application. You know, what sort of consistency model is used below. And similarly, this is quite famous, this triangle, the blockchain trilemma. Vitalik Buterin has talked about it a few times. And it means that there is a conflict between security, decentralization, and scalability. And it's not possible or very difficult to scale a blockchain extremely well while at the same time maintaining security and decentralization. So if you have a blockchain application, you have to think about this. Do I need very good security, or can I relax security a bit, for scalability? Or do I really need decentralization as much as Bitcoin needs decentralization? That's something that has to be taken into account. Okay, so that's all for now. Any questions on this?
Questions?
Just wanted to thank you. It was really a great presentation, and I'm saying it with the whole conviction, because it's a while already that I'm following blockchain, and I'm not a specialist. I'm not a technician. I'm not an IT engineer, and it's true that there is a lot of hype around the subject, and most of events I so far participated in are like about how fascinating, exciting, and whatever that is, which is great. I really like it, and obviously it's awesome to participate in such a revolution, if I can put it that way. But I was always like a little bit suspicious, and I was like, well, can it be really that perfect? Actually, you see what I mean? And I was like, it's just impossible. You see what I? So I'm really happy that there's people like you who actually dig a little bit deeper, and from this level of excitement go in depth and can share this kind of insight. So thank you very much. That's only the only comment, so I can't say anything else. I don't have questions. It was very complete. Thanks.
Thank you. Well, actually, it might have been a mistake to put me on first, because my dampen enthusiasm a bit here.
Thank you for the session. My name is Apurva. I'm from IBM. Just out of curiosity, I want to know. I'm not an expert in blockchain though. So let's say I have an blockchain platform solution, and I want to enroll all of the blockchain members. What are the 5 key security parameters I should check before I enroll a member in the blockchain? Can you highlight on that?
So you're talking about like a private blockchain scenario,
yeah,
where you have to authenticate users. So obviously that depends on the application actually, but obviously one of the key factors is that you want to know who they are usually. So you want to do all your due diligence on that, and you want to give them access to what they're supposed to have access to, right? It's fairly similar to traditional cybersecurity. Don't give anyone access to more than he needs. Yeah, and that's about it. I can't come up with a list of 5 out of the head of my right now, but I suppose it's not too different to other security policy
other than the
related
the regular that we use. So is there a kind of a privilege access can be given to a particular member or a peer vis-a-vis not to the another one? That kind of a access control?
Yeah, I mean it depends on which platform you use, but in these consortium blockchains, software like Hyperledger Fabric, that they have, they use different channels and different ledgers for different levels of access control. So yeah, that you can make it more granular in this type of software. You can't on something like Ethereum on the public network.
Okay. And maybe also with respect to limits on the API calls that the member can make in the overall transaction, that also can be throttled.
Oh yeah, of course you can at the application layer of your blockchain application you can do all sorts of traditional user management.
Oh, thank you.
I'm equally thrilled by what you told us. I think it really shows that you have done your homework and you have really gone to the depth of these issues. Can you expand a little bit on the front-running problem? Because the main use case of blockchains is in finance, is for tokens, and tokens are being traded on secondary markets. And you just said before that a blockchain-specific problem is that everybody can see what's upcoming as a transaction, so you can beautifully design a front-running attack on the trading platform on the secondary market. I didn't understand the technicalities of why everybody can see things, why it takes so long. Can you expand on that a little bit without going too much into cryptographics? Just
Yeah,
for us. I'm a lawyer as a background.
Yeah, I mean, basically transactions are completely transparent, so you can, it's difficult to read it manually, but you can write a program that tells you what the transactions that are submitted to the network are meant to do. So if you suddenly see that there's 300 Bitcoin going to be sold at a certain price, and that is visible for a while, you might get in there before the price changes, and you might exploit that. And it's particularly a problem with these decentralized exchanges which work with smart contracts, right? But there are ways around this. It's just that sometimes the actual designers of the platform are not aware of this, or realize afterwards what is happening. So there are things like a commit and reveal scheme, so you can actually have a sort of hidden transaction. So you just publish the fingerprint, the digital fingerprint of what you are meant to do. And once that is accepted on the blockchain and cannot be undone anymore, only then you actually reveal what you were meant to do. So that's a cryptographic technique. So you actually prove what your transaction was expected to do, and that's often implemented in smart contracts.
So the transaction would be done outside and only then executed into the blockchain once it has happened?
Yeah, you basically you divide the transaction in two. The first one is you're committing to do something at a later stage, but you're only sending a fingerprint of that actual transaction. Or it's a cryptographic way of proving that what you sent in the first transaction is the same as in the second transaction.
So it can be addressed, technically speaking. It's like you sign the futures today, and the futures, then 10 minutes later you execute the futures actually. So you basically encrypt the futures on the blockchain, the promise that you will buy at a certain price.
Yeah,
but you can't see really what it says, and then it's executed.
It's similar to this.
That's very interesting.
I do have one question. So you were mentioning a few best practices that are currently out there in order to prevent the main flaws that have been highlighted. What is the current state of play in terms of documentation for those best practices? Are we at a level that is sufficient? Are most of the flows currently being mapped and well documented so that people can avoid to make them again? What is the current state of play?
Yeah, there are a number of good resources. I mean, I'm particularly involved in smart contract programming, so I know of a few libraries which are community audited. Well, they're audited by audit firms, and they're also community audited in that they've been open source for a while, and a lot of people have looked at them. So one of the best practice guidelines is to reuse smart contract code whenever you can from one of these audited libraries. And there are quite a few resources. I know Consensus has a very good webpage on smart contract programming, and Open Zeppelin does. And the problem is that the protocol is still developing. So as I said before, for me it's worrying that we change the Ethereum protocol, even within version 1 of Ethereum, so that existing smart contracts stop working. And there's not much what you can do with really well documented best practice guidelines there, because they keep changing.
One last question?
Hi, I would just actually like to sort of ask the same question from the other point of view. So I have a friend in Switzerland who founded Validity Labs. He does smart contract auditing. And I remember him complaining to me a year and a half, 2 years ago, that the code he was seeing, people seem to be very, very ignorant of basic best practice. My question is, do you find the community more sophisticated now, or are people getting better at this, or you have the same old problems again and again?
Yeah, I think it's improving, but my view is obviously biased because I see projects that contract us to do an audit, so they're actually security conscious, right? So the problem are probably these projects that don't even think about having an audit. But I think one of the problems with blockchain, the ecosystem, is that some of these things are not new, right? Like overflow. The overflow is one variable overflows, and it's like the mileage meter of a car, just going to zero when it reaches its maximum. And that can be exploited in financial software, and you know, people were aware of this in the 70s when they automated financial transactions in traditional banking. And it keeps happening now in smart contracts. Why? Because people don't realize that they're actually dealing with a financial application that needs these stringent security requirements. And a lot of this is due to sort of the startup nature, you know, the young people with a really good idea, and they just start programming and sell an MVP, get some funding, and then they think about security afterwards, which is obviously good, but it has its implications when you're moving millions around on the blockchain.
Okay, excellent. Thank you very much, Stefan, for this presentation. And I would propose to directly jump into the next topic, which is actually very related and will allow us to go deeper into the question on one specific aspect. So thank you again, Stefan, and please welcome Johan.
Good morning, everybody. Thanks for the introduction. So my name is Johan Honig, and I'll be giving a talk about security analysis, and specifically how security analysis can be applied and used for these applications, these smart contracts that run on the Ethereum blockchain, but it in theory also applies to other blockchains which support these smart contracts. And I'd like to thank the previous speaker for introducing and explaining a few concepts which will make this presentation easier to understand. So a little bit about me and MythX, where I work, is I'm a security researcher and engineer at MythX. We are part of Consensus as a whole, and kind of what we try to do is take this security analysis and make it easily accessible to developers and users of the Ethereum ecosystem. So in this talk, this is kind of the general overview of what I will be talking about. I'll be giving a brief introduction on, or overview of smart contract security, and you'll see some overlap here with the previous talk. And then I'll go into the challenges of smart contract security and how we can use automated analysis to answer those challenges. And in the end, I'll come up with a brief conclusion. So, smart contract security. Let's start with the smart contracts. And like the previous speaker introduced, smart contracts have some properties which they inherit from the blockchain, and these are favorable for some security-related projects, and those are like immutability, the censorship resistance. The other properties are like smart contracts are visible by the entire, by all the participants in the Ethereum blockchain, and they usually are high-profile applications, like banking applications, like exchanges, and this makes them targets for hackers. But this also gives them very high security requirements. The other thing to consider here is that smart contracts are still code written by humans, and there will be, therefore, often be bugs and vulnerabilities, and we want to not have that in our smart contract systems. So, to give a more high-level example of what a smart contract could look like, I have this natural language smart contract here. And this is in a hypothetical situation that I have a couch that I want to sell, and the first person to give me 300 euros will get the couch. Now I can encode this into a smart contract, put it on the Ethereum blockchain, and that's kind of the first step. Then some customer comes along that really wants my couch. He sends me 300 euros, and I give him the couch. So this is kind of the best case scenario that could happen. But you might already see that there's some edge case in this contract. Specifically, only the first person to send me 300 euros gets the couch. The second person doesn't get anything. He just sends me 300 euros. And at its base, this might not seem like a huge problem, but we have front running, like the previous speaker was talking about, where I can send a transaction and try to be quicker. And then we get the following situation where I still have the contract on Ethereum, I get a potential customer, and he sends me this 300 euros. But I see this happening, and I'm really quick. I also send myself 300 euros and make sure that my transaction is accepted before the other ones, and then I get the couch because I'm the first one to receive the to send the money, and I still get the 300 euros from the potential customer because he has sent me this money. So this is an example of what this front running could look like, and later on in this presentation I will go into how we could possibly detect that this smart contract has an edge case embedded in it. Unfortunately, this is not hypothetical, and the examples I'll be giving you are also given by the previous speaker. So the first one is the parity wallet hack, and in this case, some user accidentally did an action where it killed a smart contract, or self-destructed a smart contract actually, which was part of a wallet, effectively freezing over $300 million worth of assets. So things can happen by accident. It can also happen, this is kind of the best case scenario, where a security researcher or a team of security researchers finds a vulnerability in a smart contract system and is able to at least report the vulnerability to either exchanges or the actual managers and owners of the smart contract system, so that they can implement mitigations. In the case of this vulnerability, I believe that exchanges disabled the trading of the token that was one of the tokens that was affected, thereby disabling any attacker from being able to profit from a possible hack. The last case is the DAO hack, which has also been talked about briefly, and this is kind of the situation where there is actually a hacker which finds a vulnerability in your system and is able to exploit it. In this case, there was a rollback in the main Ethereum chain, so no actual facts, but there are other breaches in Ethereum history where this didn't happen, and there were actually a lot of funds permanently lost. And this kind of raises the challenge: what can we do to resolve this risk? What can we do to prevent these incidents from happening? And automatically forwards. So kind of the main practice right now is the use of a security audit or a security review. And what this generally looks like is a team builds their smart contract project, and at the end of their development life cycle, after they've tested their project, they go to an auditing firm and they ask the auditing firm to review their project for any security weaknesses. And this firm generally reports like the critical, informational weaknesses and issues in their projects, and then they fix it, and afterwards do a little check if everything is okay now and upload the system to be used. There's no doubt about the merits of this system, but there's an issue in that it's quite expensive to really do this. And for this reason, people sometimes don't choose to do an audit or only do an audit at the very end of their process. While it is actually beneficial if you could have this security aspect of development integrated into the life cycle of a smart contract project early on, thereby catching the bugs, issues, problems that can potentially arise at the moment that they actually are implemented, rather than at the very end when it's most expensive to fix them. So this is where program analysis can help it come in. Running program analysis itself doesn't really cost any human resources, only computational resources, which is a fair bit more cheaper. There's one slight downside with some of these techniques, and that's that they have a range in automation. So some techniques require some setup, and some techniques are fully automatic. And at MythX specifically, we look at these automatic analysis techniques. We really like them because they don't need any setup. You just take them and run them on your system, and you get immediate value. So the techniques that are listed here are the techniques that we specifically have decided to use in our own platform. They kind of play into each other's weaknesses and strengths, and together make like a powerful analysis backend that can find a lot of these weaknesses and vulnerabilities. And what's important about these techniques for understanding how bug finding or security analysis works is that they basically take all of them, take a smart contract and try to explore the different possible interpretations and ways that a contract can be executed, so the flows through a contract. And during this exploration, they allow us to check for certain patterns and rules. And these rules and patterns we can formulate to indicate vulnerabilities. And how we come to these patterns is what I want to talk about next here. And this is kind of the generic workflow we have. So you kind of start out with a new vulnerability class that is discovered, like reentrancy or overflows. Well, overflows is maybe not a really new vulnerability class, but we can work with it nonetheless. And there's this really nice initiative by the Ethereum security community, which is the Smart Contract Weakness Classification Registry, SWC for short, which is a repository of these different smart contract weakness classes, which includes documentation on the description on these vulnerabilities or weakness classes, examples of how such weaknesses look like in real-life contracts, and possible mitigations. So what we do is we take such vulnerability class and we make a more formal description, a more formal model, which we can later on implement in our tools. And what such a formal model actually looks like, I'll go into in the next slide. But we end up with this set of logical rules, basically, that precisely describe the weakness that we're looking for. And using this model, we can build detection modules and teach the tools or techniques to look for this vulnerability. So we have a vulnerability class, we make a model, we teach to the tools, and then we can leverage this exploration of the behaviors and the interpretations of the smart contract to actually start looking for these vulnerabilities. And to explain what a formal rule or model could look like, I want to go back to the example I had in the beginning, which is the following. I had the couch that I wanted to sell, and the first person to give me the 300 euros will get the couch. Now, the way that I explained the actual exploitation leveraged a front-running attack, but the actual issue here is the fact that I can transfer money to the contract and not receive anything in return. Front-running is one way where this can result in a bug, but it could also happen that two users try to buy the couch in parallel, and that will also result in an issue. So basically what I want to say is that I always want to either get the bank or get a refund. And this is kind of a natural language equivalent of the rule that we would implement in our analysis tools. So we teach our analysis tools in this case to look for situations where a customer sends 300 euros or any amount, actually, really, then, and the customer doesn't get anything in return. So no refund and no couch. And if this is the case, we will report it to the user. And so we've taken this smart contract weakness classification, the SWC registry, and right about now we have like a coverage of 80 or 90%. I'm not precisely sure of all these classes that we are able to report issues for, and we're always trying to extend that. And for these cases, we can report to the user that they are present in their programs, which is really nice. And actually, the 3 examples I showed, and many more, of real-world incidents, security incidents, can actually, in some cases, be captured by using this automatic analysis that we have right now, and sometimes even the automated analysis that was available at that time. So let's now go into the different places where we can use this technology. And kind of the most straightforward place where we can use it is in the development. The developers can use this technology to get quick iterative feedback. They basically have, or we'd like to think of it about like having a security specialist sitting right next to you. Of course, this isn't really the case. A security specialist would probably be able to give you more specific information about the security of your system, but this is as close as we can get. And we provide this quick iterative feedback with in-depth security information about your system, which allows you to catch these bugs early on and tackle security of your system in the beginning of your life cycle rather than just at the end at this audit phase. The second part, which happens in smart contract development, is this testing phase where you're kind of done with the development of your project, so there's not these quick iterations, but you're really testing your system in depth. So in this case, we don't need to constrain the analysis techniques within a tight bound. So we can give them more time, more resources to really find all the edge cases that they can find in the smart contracts. So we can give it a day, maybe give it 2 days, to give more assurances. So these are 2 kind of separate use cases. Then we also see a use case for smart automatic analysis in kind of creating visibility into the security and risk of a smart contract to users other than the developers themselves. Because as a normal user, it's really difficult to really know whether the smart contract you're using is actually secure. Sometimes, not always, the firm that deploys a contract releases a security audit report, and this gives you some assurances, but it's really hard to, difficult to read these documents if you're not an expert yourself. So what we can do with this automatic analysis is signal to users about whether we find any critical vulnerabilities or not, and thereby give some assurances and insight into the actual security of the system. And lastly, something I didn't note here, but which I list on the slide, but which I think is really interesting as well, is these techniques that we use ourselves, where we have our own formal models that generalize weaknesses and vulnerabilities. These techniques can also be used by auditors to extend their capability of finding vulnerabilities in the system they are auditing. So what they can do specifically is formulate these models specifically to the business logic of the contract they're auditing. So in an exchange, you might want to look like for certain properties that always need to hold. You can see the property I just talked about with the asset transfer. This is a somewhat ungeneric property, which is about like the transfer of assets, or maybe a sales system, and doesn't apply to exactly all smart contracts out there. So in this case, an auditor is able to use these techniques to empower themselves with it. So in conclusion, these automatic analysis techniques allow you to build security in from the start and give the developer this security information and review at the beginning of the process, throughout the process, and not just the end. And it's super complementary to the use of security reviews and audits. And the second thing is security analysis can help create this visibility into the security of these smart contract systems. And it already skipped to the next slide. Thank you for listening. I think there's some time for questions now.
Questions? I will start then. So I have a question regarding regarding your experience and feedbacks that you get from the developers that work with Methex. What is the current state of play regarding the gap between what they can do with Methex and what they need to do in order to reach production in the end? I definitely understand that this is a tool that comes from the beginning and that is meant to really build but not replace the needs for audits. What is the gap between the two?
Okay, so yeah, now it works. So kind of the main difference between what I'd like to think between security analysis and an audit is the following. In a security analysis tool such as ours, it is me and a group of security experts that generalize these vulnerability classes and write the models for the generic vulnerabilities. And we can look for those vulnerabilities. But if you have a system and the bug in your and you have a vulnerability in your system, and the vulnerability is not really such a generic one as we talked about today, so like reentrancy or an overflow in your contract, but rather a logical one, like a mistake in how you design the contract, then it's not easy for us to look for those, because we kind of need to distinguish between what does the developer intend and what are the patterns that we know are vulnerable. And humans are kind of amazing at this interpreting of what other humans mean and what the contract that is then supposed to do, so then they can look for these logical things. And this is also where the security analysis can extend the normal audit, because security reviewers and auditors are able to teach the tools to look for these business logic specific bugs and vulnerabilities. So, cut out randomly. So, yeah, okay. So, on its own, MythX will just help you to find these generic vulnerabilities, which are very important, of course. But by itself, only looks for issues in your business logic if you write specific assertions for them in your code. And a lot of developers do this, so we are able to find some issues in the business logic of your code. And security reviewers are really good at finding issues in the logic of your code. And, well, together they'd be even more awesome. That's kind of where we are now.
All right, thanks. Any questions from the audience?
Hey, I have a question. So I know there's Mithril Classic, right? Which is the open source free version, basically. And MythX is not for free, right?
No.
Okay.
Well, there's a free mode, which has limited capabilities compared to like the premium version. So there's a limited number of SWC categories that will be reported, for example.
Okay, because my question now is like, what is the difference now between Mithril Classic and Mithril X and MythX? So in the sense that if you add a new model to MythX, will you also add it to Mithril Classic, or will you just say like, okay, the community is now a tool for the community needs to extend it, we will not take care of it anymore?
Okay, so I'd like to start out with this first part and maybe explain more of the difference between MythX and Mithril. MythX itself includes multiple tools, so this is Mithril Classic, which we've called Mithril again. This is our symbolic execution tool, and this is kind of, I believe we started 2.5 years ago with this, and this has been open source since the beginning. And this is a tool that allows you to find these vulnerabilities, but it's only one part of our backend. Our backend now also consists of 2 other tools, one that does gray box fuzzing and one that does data flow analysis and abstract interpretation. And like I said a few slides ago in the presentation, these tools have different strengths and weaknesses, and they are very nice together. They're complementary, and they're, for that reason, without excluding like detection modules from Mithril, the MythX platform will still be more powerful. In regards to actually releasing detection modules for Mithril and MythX, we're not exactly sure about how we're going to approach it. Right now, all the detection modules that are available in Mithril are also the ones that we run in our backend for Mithril. And we are planning to, like, one possible approach that we could take is like this delayed release approach, where we build a module, we run it, our paid users get it for a year or a few months, and then after a while we release it for the public.
Okay, thank you. That's what I wanted to know.
Okay, any last question maybe from the audience? Yes, please.
So you model the weaknesses of smart contracts in your system. So what are your views on going one step further, like modeling, allowing the developer to model the actual intended behavior? That's sort of more similar to formal verification.
Yeah, so You can already kind of achieve this by introducing assertion statements in your code. So one of the things that our platform does, it looks if there's any possible way that we can reach an exceptional state, so a state that shouldn't happen in the system, and then we'll report that. So in this way, the developer or an auditor can lead the analysis to find these business logic specific cases. We are also interested in allowing the developer to specify more and maybe use like techniques like more formal verification techniques, and allowing our tools to interpret and help with that process. But our offering right now and the current like the tools that we currently see being used are these automatic analysis techniques, because they don't require any education. Like anybody here could go to our website, get a plan, and use the tool and get the security feedback and read it and hopefully understand it and do something with it. If you look at more formal verification approaches, so there's a few projects out there right now that do this. So you have Verisol, I believe, the K framework, and people out behind Securify are working on similar projects. These aren't necessarily easy to use yet, or at least as far as I understand it, they are more difficult to use than like just a tool that you don't need any prior education for, that you can just run. So yeah, I hope that answers your question.
Yes, thank you.
Last question. So, one quick question. As a part of this overall analysis tool, yeah, let's say if I want to implement that in the solution, do I have a flexibility to create my own security policies and apply that in my tool chain?
Could you give an example of what
Yeah,
you mean by security policy?
Yeah, so like from the enterprise standpoint, let's say I have certain custom security policies that I want to enforce in my blockchain solution. Yeah, and there's a custom configurations that I have to imply on the at a user or at an interface level, and I want to enforce that policy whenever I develop any solution, and it goes through that security check gate and it gives me whether I am compliant or not, so that I can put it back to the UAT and production.
Okay. So so your question is your question the following, where you have a company policy,
yes,
and you're wondering how if you could integrate such a system as like a barrier or like a compliance check in such a policy?
Yes, yes. So I have my
Oh, yeah,
company
definitely.
policy and I can
Yeah, definitely.
use this tool.
So one of the things that you could do is, well, this is more like lower level and like a development policy, but if you have a pull request, or if you want to release a new version of your software, this is usually done in continuous integration, and you can extend this with a step where you call into our system, or use any security analysis tool really, and interpret the results and have some requirements. Like there cannot be any critical vulnerabilities that these tools find in the software before we release it. So you could also, I guess, extend this to your corporate policy, in that you require a product to have certain levels of security based on the results that automatic analysis tools are able to give.
And it can go deep to the protocols and ports and network.
So specifically, we only look at these smart contracts. So we specifically look for vulnerabilities on the programs that are executed on the blockchain. If you're looking for finding issues in protocols and maybe application layer security, then our tool specifically won't help you with that, but there's other security analysis tools that can help you there. So there's some form of verification approaches and I'm not able to recall their specific names or the tool names, where you can formally verify protocols. You can do similar things that we do for smart contracts, but for web applications or JavaScript applications, and there find possible issues in there. But we're specifically focused on these smart contracts because these are kind of the most critical part of your blockchain application. And if there's a vulnerability in the smart contract, that's a big problem, right? Like there's millions that get lost. So this is, to us, like the most important part of the chain, but there's definitely analysis techniques that you can apply on the other parts, on the other parts of this, like blockchain application stack.
All right, thank you. That's my question.
All right, thank you very much, Joran, for your presentation. Thank you very much to the audience for your questions. Please, a round of applause for Joran. And we are directly going to continue on the next topic with Stefano from the University of Southampton, who is going to dive again deeper into security aspects. I just want to mention that, so of course there are many experts here in the room. However, there are some people who maybe not are very familiar with some of the concepts that are being presented here, or maybe only mentioned here. So please, in the audience, if there are any aspects that you're not familiar with and would like to ask, please feel free to do so. Don't feel ashamed. There is absolutely no shame. So please do so. Feel free. I'm going to. This is not the right one. Yeah. Okay.
Thank you for the introduction. Hello everybody, my name is Stefano De Angelis. I'm a researcher at the University of Southampton in the Cybersecurity group. I come from a distributed system background, and the last years I focused on the interesting blockchain technologies. Today I'm going to give you a talk about the security aspect and open challenges of blockchain and consensus protocols inside these systems. So a brief outline of my talk today. First of all, we're going to see some important topics in the blockchain scenario, the security requirements of this technology, the challenges, and the differences between blockchain systems. Then we will gonna see something more interesting inside deep the technology in the consensus algorithm of the blockchain. We will see two main families of consensus protocols, like lottery-based and voting-based protocols. We will go then into the Byzantine fault tolerance and the proof of authority. Finally, I will show you some security analysis techniques we adopted for the evaluation of these platforms. And then we can have a discussion about open challenges and opportunities for the blockchain technology. So, first of all, let's introduce the concept of multi-party infrastructure. We have in our business infrastructures, we may have some distributed network of parties that aims to interact each other to access from some services distributed inside the system, some data shared, or just notification of other applications. These parties may not trust each other and need to communicate over a shared infrastructure. Some example, we have the financial services, Bitcoin, for example, when you are sharing and transacting value, economic value, cryptocurrencies. In the logistics, very important, the multi-party infrastructure where we can have different parties participating in a supply chain, sharing some transactions about the production of the products. Then in the Internet of Things, of course, we have a network of distributed devices sharing information collected, sensed, and they need to share it over a platform that must be secure, because if some node, for example, in Internet of Things, some device is corrupted, we cannot trust of these informations. How we did so far today? We are managing multi-party system nowadays with centralized solutions. We are using centralization. What does it mean? In these architectures, we have a centralized party acting as a trusted third party between the multi-party system. The objectives of this third party are to regulate the interactions between the nodes of the network. It has to manage the transactions and guarantee the correct behavior of such systems. Where are the problems here? There are some drawbacks, because when you're relying on a trusted third party, you must trust on it by design. Who knows if the party is not corrupted? And what happens if someone corrupts the party? You cannot rely on your system anymore, so you are in troubles. Then, of course, this party represents a single point of failure. So if you attack this party, your system won't be available anymore. So how can we avoid decentralized third parties? And that's where blockchain comes. A blockchain is a decentralized, fully replicated ledger of shared transactions inside a multi-party system, essentially. So we have a distributed network, peer-to-peer network of nodes sharing some information. The ledger collected among the nodes is produced and updated collaboratively by all the nodes of the network. In this way, the technology is very interesting because it distributes trust. So we don't have anymore the trust over a centralized entity, but we distribute the trust among all the participants of the network. The participants achieve consensus and order the transaction according to a democratic algorithm. The blockchain is said to be secure because we have cryptography and because we have the validation of transactions. So anyone says that blockchain is the future because it's the most secure platform we have nowadays. But it's really secure, the blockchain. What about the performance of the platforms offering blockchain services? What about the security of such platforms? So far, we have two big types of different blockchain systems. We have the public blockchains, where any node of a peer-to-peer network can join the network and start participating in our network, like updating the ledger, reading the ledger, and so on and so forth. Examples, Bitcoin, Ethereum. So our public blockchain, anyone can download the client and start participating inside the network. On the other hand, we have the private systems, private blockchains, where to access inside the network, you need a sort of authentication rules. You cannot access by design, but you need some authentication techniques to enter inside the network and start participating and collaborating. Usually, these are useful in organizations for private industries that want to build some multi-party system infrastructure among a predefined set of nodes. Example of these technologies is the Hyperledger Fabric. Then we have a distinction in permissioned and permissionless. We don't have permissions inside the public blockchains, so anyone can join, anyone can read, write, and update the ledger. In permissioned blockchains, we have permissions. So if you access to the blockchain, may have like just reading permissions, or in other cases you can have also the write permissions. Also participate in the consensus algorithm and update the ledger shared among the network. So speaking about security, the blockchain can be summarized as a 4 layers architecture. We have the application layer, we have the smart contract engine layer. We already seen with a colleague the problems related to the smart contract security. And then we have 2 layers that are very important, which are the network layer and the consensus layer. These 2 layers are important in the terms of security because strictly impact the performance and the security of a system. So if you corrupt one of those layers, you cannot go far from the others. your system is not available anymore, not secure. Blockchains can benefit from many techniques developed for reaching consensus, replicating state, broadcasting transactions, and more, in environments where network connectivity is uncertain. Nodes may crash or become subverted by an adversary, and interaction among nodes are inherently asynchronous. This is a very nice sentence from Kashin and Vukovic, which are two of the most important researchers in the field of distributed systems and blockchain, and fix the very important points related to consensus and networks. We are working on real scenario networks, the internet. We cannot trust inside it. We don't have trust inside the internet. We can have problems like delays, adversaries, attack, and different things. So the consensus protocol must be resilient to such systems. What is a consensus protocol for a blockchain? In a network, like a peer-to-peer network like the blockchains are, the nodes achieve consensus, so agreement on which transactions to put inside the ledger and the order of such transactions. So the order of such transaction is called atomic broadcast among the transactions. To do so, they run this distributed consensus algorithm. A distributed protocol must guarantee, by design, safety and liveness properties. Safety has integrity, so we don't want to corrupt the data shared. Liveness in terms of availability of the system. So I want my system to keep responding me, keep serving requests from clients. These two properties must be evaluated in different network models. We want to refer the classic internet model where networks are asynchronous under different trust assumptions. And we need to evaluate also the presence of possible adversaries, the so-called Byzantine nodes. In this case, so that's why we are looking into the Byzantine fault-tolerant consensus protocols that have been studied for 20 years or more, but nowadays are going back to the studies because the interest of blockchain. So the consensus ensures the trustworthy and the reliability of a platform, and it's very important. In blockchains, we have two big families of consensus protocols. We divide the consensus in lottery-based consensus protocols and voting-based consensus protocols. So the lottery-based consensus protocols are used in very large networks, so it makes sense to use them in public networks. Essentially are lottery-based, so a probabilistic election of leaders inside the network. When a leader is elected, can propose a block, but this is strictly probabilistic. An example is the proof of work. Voting-based protocols are the classic Byzantine fault-tolerant protocols. They rely on a voting mechanism between the replicas. We know that they are feasible in small networks, smaller than the big public networks, so that's why I put here permissioned networks. They require very message-intensive exchange between the nodes, because they exchange messages to elect a new leader, the leader will propose a block, and the agreement will be achieved on the message or transaction. The most prominent, the most famous implementation is the PBFT, Practical Byzantine Fault-Tolerant Protocol. Let's see two examples of such lottery and voting-based architecture. The proof of work, we all know about the proof of work. It's a probabilistic protocol where miners run a competition. When a miner wins the lottery, he can propose a block. The problem here is that to win the lottery, the miner has to put a lot of computational power and do some mathematical calculus to achieve the final result. This is good for trustless network because probabilistically, eventually, a miner is elected that will propose a new block to the network. The rest of the network can verify the result received and accept or reject it by the verification. The problem here is that the computational intense requirements of this protocol lead to high latencies and so low throughput of the system. For example, in the Bitcoin, we have like 10 minutes for the confirmation of a block, and the throughput is around 4-6 transactions per second in Bitcoin. In MasterCard on Visa, we have thousands of transactions per second. So the proof of work guarantees liveness. Why? Because it's highly replicated among the network. So we have a public network, very replicated. But the safety of the system, is the proof of work really consistent? We always hear about blockchain is immutable. Blockchain, data on blockchain are tamper-proof. No one can change nothing about the blockchain. That's true in part. The proof of work is a probabilistic algorithm. So probabilistically, you will have a miner elected inside the network. But at the same time, probabilistically, you can have two miners elected at the same time inside the network. In this case, the two miners can propose a block and create a fork, so-called fork inside the blockchain network. A fork is when two parts of the network have different views of the blockchain at the time t0, for example. In Bitcoin, or in proof-of-work implementations, the forks are eventually resolved. This means that eventually the network will converge to a single ledger. In Bitcoin, for example, the trust on the longest chain of Bitcoin. So if a block is on the longest chain on Bitcoin, it's considered final. Final means that cannot be changed anymore. Once a block is proposed in Bitcoin, has to wait for 6 further blocks to be considered final. That's a very important property for the evaluation of security of a system. So safety in proof of work is guaranteed eventually, because we have to wait 6 blocks before consider a block safety and final, sorry. On the other side, the other family, we have the PBFT. It's very famous, very used in distributed systems. PBFT, it's a 3 voting phases protocol where replicas of the network elect a leader. For example, here we have the node 0 as a leader, and then when the leader proposes a block, they exchange a sort of messages to agree on the total order of the message, in this case the blocks in blockchain, and the validation of that message. Once the agreement is achieved, all the nodes commit the block immediately. This means that, going back here, the consensus finality here is just eventual. Here is immediate. Until the nodes achieve agreement on a block, they commit immediately on the blockchain. This works and safety is guaranteed until we have in the network the number of 3f plus 1 nodes, with f number of faulty nodes. So we can tolerate up to 1/3 of faults inside the network. The liveness is guaranteed eventually here. Why? Because the protocol works in real networks, but in synchronous periods. When we have asynchronous periods of the network, for example, like Stefan introduced this morning, a partition of the network, in this case, the protocol may stack, so won't go on. The important thing is that in this period of asynchronously, the safety is guaranteed, so no one can change anything on the ledger. That's why the PBFT is good. Problems. PBFT requires a lot of messages, you can see. So if we have 3 nodes, it's okay, it works very good, and the performances are very high. What happens if we have 100, thousands of nodes? Performance degrade, because we have to exchange a lot of messages inside the network. So these 2 families are good, have some advantages and some disadvantages. In the lottery-based, we have these big networks running for a competition. We have eventual consistency inside the network, but high availability. The performance are very bad. On the other hand, the voting-based, we have a high throughput, strong consistency, despite the availability of the system, because the system is installed, and very bad scalability, so we cannot work in large-scale networks. So what happened now in the blockchain community? A lot of technologies started to propose their own consensus protocol based on different assumptions and different considerations. The main goal of these platforms is to achieve good performance, good security, good scalability inside the system. So they are trying to put their protocols in the middle from the lottery-based and the voting-based protocols. A lot of these systems states that they support and they tolerate more faulty nodes than the PBFT. That's strange because the PBFT is proved mathematically that's to be the optimal solution nowadays in distributed systems. So these protocols are very interesting, and a lot of proposals in technologies we have now. We call these protocols hybrid consensus protocols, and are very, very prominent technologies. From those, we picked one, the proof of authority consensus. The proof of authority takes something from the proof of work and something else from the PBFT protocols. So they start from the evaluation of the consideration of eventual consistency, where we have just we have to wait a period until a block is achieved, until a block is final. But we want to achieve in this case high performances and keep the scalability at least, not without degrading the performances. The proof of work works in a network, in a permissioned network, where we pick a subset of nodes called authorities or validators. These validators run the consensus, not all the network. The validators run a mining rotation protocol to be elected as a leaders, dividing the time in steps. So at each step, we have one leader that is in charge to propose a block. Differently from the voting-based, in the lottery-based, where the leader is elected probabilistically. Here is deterministic. So we elect a leader at each time step. We have two implementations of these protocols in two Ethereum clients, Parity and Get, and they're called Aura Proof of Authority and Click Proof of Authority. I will briefly show you the functioning of such protocols. The Aura is a very interesting protocol, but has strong assumptions on the synchrony of the network. We have a subset of nodes called validators. The time is divided in steps. So at each step, time T1, time T2, we have a leader. When the leader is elected, he's supposed to propose a new block. The leader proposed the block in the block proposal phase. Then all the other replicas, authorities and known, also the clients of the system, accept the block. Wait, the block is not committed on the blockchain. It's accepted by the node. Why? What happens if in the block acceptance phase nodes disagree? So there are different leaders. It may happen. So in that case, the authorities start carry a voting mechanism, trying to vote out the misbehaving leader. A leader is misbehaving around these three rules. Once the authorities achieve consensus on the misbehaving leader, they will kick out from the authority subset the leader. As I said, a block is not final for that reason, because there can be some forks. The finality in Aura is achieved, as in Bitcoin, waiting for something. In Aura, they are waiting for a majority of further block proposed inside the network. So if I propose a block, to be considered final, he has to wait n block, okay? A majority of the network, so half n plus 1 blocks further. It's like the longest blockchain of Bitcoin. Click, on the other side, is quite different because it's not relying on the synchrony network. At each time, we have one leader computed mathematically, but a subset of possible leaders that can propose a block. In this case, we can have fork as well, because we can have the leader proposing a block and at the same time also the other possible leaders proposing a new block. In this case, we can have a fork inside the system that eventually is resolved by some techniques of Ethereum clients. There is a protocol called Ghost protocol who gives scores to each block. The blockchain with the highest score is the real blockchain, the blockchain we have to trust. The developer states that this protocol should resist to a minority of possible Byzantine nodes, so attackers, and keep guaranteeing safety and liveness inside the system. Safety is only eventual because we can have forks. But look at the message exchange of this protocol. It's very easy because a leader is elected, the leader proposes a block, and the block is committed to the blockchain. Then, eventually, we will resolve the possible forks on the system by the use of ghost protocol and checkpoints. So, just a small comparison, looking at the messages exchanges inside the systems, we can see that Click and Aura can be more performant. More performant because we have less messages. So, increasing the number of nodes inside the network could affect the scalability, but is better than the PBFT. So they are very promising and they are very performant, keeping safe the system with a minority of attackers and no 1/3. Perfect. We solved the problem of consensus in blockchains. That's not true. So proof of authority seems very good performances as a hybrid consensus, but what about the security of the systems? Are the systems secure? Can we trust about the systems? Seems that we can trust them, but no. So we conducted an analysis with the CAP theorem as well again, as we see this morning, so I will skip this slide. We know the consistency, availability, we have to pick inside a partition tolerance system. But I want to show you again the blockchain layer. We saw how the consensus is important. Now let's go down to the network. What happens in your protocol if you have network problems like partitions, delays, Byzantine nodes? In Aura, it's perfect because they state that any minority of attackers is supported by the protocol. In proof of authority, sorry. In PBFT, it's proved mathematically that is 1/3 of attackers to be supported. We want to investigate what happened in the new proposals, because these proposals are trying to sell to the business companies their product, saying that they are better of the other protocols. Are the ledger consistent in these protocols? The transaction reach finality in these protocols when we have network problems. So we studied the Aura protocol, and we found an attack, a vulnerability of this protocol. Aura is a protocol running among validators. We have a small subset. I will go fast on this. This is quite technical, but we have two subsets of validators, A1 and A2, inside the Aura network. What happens if we have desynchronization period between these two groups? We can have small desynchronization periods. Working. Yeah. We can have small desynchronization periods in these networks and these two groups. If a leader proposes a block, if a leader from one group proposes a block in a desynchronized network, the other group may see this node as not a leader anymore, or not yet a leader. So the nodes of this subset will vote out the leader because he's misbehaving for them, because the problem of desynchronization. And this perfectly works. But what happens if nodes cannot achieve a majority inside the subset of node voting out this behaving leader? So if we cannot achieve this result, so we cannot vote out the misbehaving leaders, we can have forks inside the system. If we have forks inside the system, it means that the blockchain are different. It means that the consistency of your blockchain is broken. So you don't have a consistent system anymore. Safety is not safe. So network synchrony assumption of Aura, for example, can turn out as a vulnerability. It was fun to see how the parity, Aura is a protocol implemented in parity. It was fun to see how parity changed the documentation of the protocol once we published this article. So with the CAP theorem, we evaluated the two proof of authority algorithms and we compared them with the PBFT. We can see that Aura and Click are AP protocols, so availability and partition tolerance. Why? Because in Aura we don't have consistency at all in eventually synchronous or asynchronous networks, while in Click we have eventual consistency, because eventually the blockchain the forks inside the blockchains are resolved. In PBFT is proved mathematically to be strong, consistent, but we don't have availability. What about the proof of work? Someone knows where we can put the proof of work in this triangle? The proof of work is an AP system, because we saw this morning the possible attacks to the protocol. It's an AP system because we have eventually safety, eventually consistency of the blockchain. We can have forks in the proof of work. What happens if we are vulnerable to the 50% attack? If the 50% attack is exploited, an attacker can change the history of your blockchain, change the integrity of your blockchain. So someone asked about the properties, 5 properties, security properties. In our draft paper, we identified some properties for the evaluation of the technologies implementing consensus protocols, and 3 properties for the evaluation of consensus protocol. In this presentation, I avoided the description of proof of stake, but here we have the proof of authority, the PBFT, and the proof of work, as we discussed, the safety and the liveness properties, and then we identified 6 properties for the evaluation of platforms. These properties comes from the SIA triad, so the confidentiality, the integrity, and the availability of your system, and then we introduce some so-called profiling properties. So properties for the profilation of the users. So the accountability, the authorization, and the client fairness. So the democratic approach the client has inside the system. Okay, we evaluate the security of such platforms from a qualitative analysis with the CAP theorem. But now, what we are going to do in Southampton, we are trying to build a framework, a general framework, for the evaluation of these technologies from a quantitative study. So we want to measure the behavior of such platforms in real network development, where we can have problems like network partitions, network delays, attackers. We are building a benchmark framework. We already have a system model, a threat model, an architecture, and the metrics that we want going to measure. And this benchmark will be able to measure different platforms and offer to the clients, to who wants to integrate blockchain in its business, a real result of the performance and security of the platforms. And it's good because you can choose the right technology, looking at the trade-off between security and performance of your system. So in conclusion, there are several consensus protocols for blockchain, because blockchain is trend, is fashion, and is fascinating technology. The security and the performances of these platforms is very important, and no one is studying yet how these platforms secure are. We focused on the consensus model and the network model of the systems, and we evaluate different consensus protocol. The proof of authority is one of the hybrid family of the consensus protocol, and we identified the synchronization problem of Aura and the eventual consistency problems inside the Click protocol. And that's all. Thank you.
So, near the beginning of the presentation, you mentioned how PBFT is proven to be secure up to some level, of course. What's the reason for other, or the researchers and developers behind other consensus protocols to not take the same approach? And, yeah, why don't people do that more often?
Why don't people use PBFT, you mean?
No, I mean, why don't they take the same approach to mathematically show...
Okay. Because show mathematically a consensus protocol is not easy. So till today, so far, no one comes out with a new research paper about this mathematical proof of an algorithm, like in PBFT. So PBFT is demonstrated to be optimal. Others have some drawbacks. So PBFT is trying to offer strong consistency inside an eventually synchronous network where liveness can be affected. Okay, we don't have other studies like proof of work, PBFT now. There are some studies with mathematical proof, but slightly different from the definitely outcome of PBFT. That's why they are trying to study alternatives.
Okay. So, and so at the end there, you were proposing to have some sort of benchmark to
Yes.
kind of replace it then. So I guess that would be one approach to solve like the issue of visibility into the security of these systems. Would it also be possible to make it, like, I don't know these techniques, but is it possible to make it easier to prove like these mathematical properties about these consensus protocols? Or is it like it's always going to be a difficult thing to do?
The way we want to do that is by experimental evaluation. So with a benchmark, you see experimentally the problems the platform have. The problem here is that most of such platforms, like Parity, like other systems, don't have a security analysis of their protocol. So there is a lack of information, a lack of analysis in terms of security and performances of their protocols. That's why with a benchmark tool, maybe we can identify the properties, like the throughput of the system, like the latency of the system.
Hi, I'm Liliana. I work for local telco operator Proximus, and I'm part of the virtual team of blockchain in my company. I have a question maybe to all three of the speakers, just to hear their opinion on a single question, because it somehow relates to all three presentations. So I didn't see anyone mentioning like other prominent projects except Bitcoin and Ethereum, for obvious reasons, of course. But for example, some properties of some projects like Cardano from Charles Hopkins, who is one of the creators of the original Ethereum. And I understand that in Cardano project, the guys are actually doing a lot of mathematical proofs and peer-to-peer validation, first on the academic level, and then looking into formal verification methods, etc., etc. So I would like to hear opinion, at least a view, and if time, from other two guys on Cardano project, and maybe the other project would be, I'm not even sure about the name. It's from Italian guy.
Algorand.
Exactly.
So far, I haven't seen. There is plenty of this project in blockchain. It's full of projects. So you have to pick one or two and focus on that. So from Southampton, we are focusing now on the proof of authority algorithm. We haven't looked yet at the Cardano or Algorand. I know Algorand is something like proof of stake. I heard about that, but I haven't had time to go deep into this technology. So we are focusing now on this, and then once we have the benchmark and the tool, we will start evaluating all the other technologies in Cascade. But yeah, it's full of new protocols trying to offer different mathematical proofs, I know.
Yeah, just to add to this, Cardano is a very good project, and it's I find it's a pity sometimes that these projects that take their time to do things properly are criticized for being slow. And there seems to be a lot of pressure also on Ethereum 2.0, and they are taking their time to do things properly. And it is cutting edge research, what they're trying to achieve, so it does take the time to get it right, and there's a lot at stake. I don't know much about Algorand, to be honest, so I can't comment on that project, but there seems to be a theme that projects that promise a lot and get code out quickly are very highly rated, and other projects that take their time to do things properly have an issue. You know, they're criticized and don't gain as much traction. And also there seems to be a big gap between academia and more sort of practical implementations in blockchain, in the industry in general. Very large companies don't take their time to do these mathematical analyses, and I'm not sure that's a problem, because you have to be practical at some point, but there's a big difference between the history of distributed computing and the mathematically proven results that are already there, and what people are doing now in practice.
Yeah, my answer is probably gonna be very similar. I guess it's just really nice to have these projects consider the approaches, like formal verification approaches, while they build their platforms, and sometimes even build them in. It's probably not happen a lot because of the fact that most of the developers behind, or a lot of developers in blockchain don't have PhDs, and they mainly build a project. But the fact that they start to think about this at the beginning allows the groups themselves to build these tools that make it easy to find vulnerabilities, to prove that there are no vulnerabilities, or prove functional correctness, make it easier for them to develop the tools. And for groups such as ours, it's also sometimes the language features or the architecture features that they choose to implement can be beneficial to us for developing those tools as well. So I think it's really nice that projects like Cardano or the other one, which I forgot the name of, think about this in the beginning.
As a point of information, Professor Silvio Macali of MIT, who's the founder of Algorand, will be a keynote speaker at Malaga, the conference that I mentioned, and they're also members of this International Association of Trusted Blockchain Applications. So if you want to see them and hear about that, please come to Malaga or come to ENAP meetings in the future.
The place to be, we told you.
And by the way, Charles Olskidson will be also there, so I'm also from DigiConnect. I want to come back to your comment about this, or your suggestion about organizing this type of benchmarking for validating the validity of, let's say, the core of blockchain protocol applications. And so I would like to get some views about how to organize it. We can have a lot of good team in academia who test as you are doing it for the time being. Should we stay always at the different infrastructure level, or should it be something that we can do also at the application level, maybe in a more restricted type of application, in order for people to get more confidence about the cybersecurity resilience of what they are proposing. So I'm really on demand about how this type of things could be organized, because this is something that we are thinking in the context of the European blockchain service infrastructure that we are developing for the time being with member states, and also this is probably something that we can support at EU level in order to have a framework where we can benchmark different type of technology. One obvious objective would be for cybersecurity reason, but it could be also for performance or other aspects. But how to make it concrete, how to make it happen, possibly in Europe? If you have any suggestion about that, it's a question for all the different speakers and maybe other participants in this workshop.
We already have a prototype for this benchmark, and what we have so far, it's a distributed system able to implement different blockchain technologies, target blockchain technologies. We are working on Parity, we are working on different Ethereum clients. The idea is to have two machines working on inside the benchmark. These two machines, one of those is the blockchain network. We are using some containerization technique to simulate a blockchain network. On the other side, we have another machine firing a workload to the blockchain. This machine will overload the system and then will collect metrics to evaluate and measure how the blockchain is performing and the security of the system. How the security? By evaluating the integrity of the blockchain. So you fire a load for a couple of minutes and then you can see what is happening inside the blockchain. So the last state of the blockchain. You download it from different nodes and you check the integrity of the blockchain. Okay. As a general purpose, we have to define a strategy for doing that. We are focusing, as I said, on the consensus and network layer. So we are building a benchmark for metrics related to consensus and to network measurements. So throughput, latencies, scalability, and integrity, and so on and so forth. Another tool we are implementing is the simulation of Byzantine nodes inside the blockchain. So we are working on the code of these technologies, trying to modify the code and simulate Byzantine behaviors like denial of service, so ignoring the proposal of a block if you're a leader and so on. With these Byzantine nodes inside the network, again, we fire the workload and we measure the results in terms of throughput, in terms of latencies, in terms of scalability, and in terms of integrity of the system. If you want to go up to the other layers, there are other techniques. At the application layer, you can build smart contracts. So you can do a benchmark framework just focusing on the smart contract of the system. Again, you fire the workload, calling the smart contract, different function of the smart contracts, and see the results and measure. First of all, you have to define your metrics, which metrics you want to measure. Then you need to define, here, the system model and the trust assumption of your system. We are basing on the internet deployment because that's where we want to deploy blockchain systems. And then the attacker model, so you can build a smart contract just to open a read and write operation in a key value store. And what you want to do, how do you want to treat this model? And then the evaluation metrics of what you want to measure. So we are doing that on the last two layers. The idea is to fire a lot of transactions, the workload, and see the result, how the network is behaving. I hope I answered your question. But yes, it will be interesting to integrate other layers rather than the consensus in the network.
My question was both about the methodology approach, the techniques that you have addressed, but it's also how to organize these things, because we
what
cannot
do you mean
rely.
How to organize?
Let's imagine that can we ask always University of Southampton to make an audit about different blockchain services? Can we ask a private company like yours to do that? Can we set up a kind of framework in order to organize this benchmarking?
Yeah, of course.
With different.
We can do that.
So it's also which type of let's say structure organization we have to put in place in order to make it possible.
Ah, okay. So yeah, collaboration with the University of Southampton. I mean, the goal of our study is to build a framework to be used. So if we want to open a collaboration with the University of Southampton, we'll be more than happy to do that with Europe. I don't know now if the time is good, but yeah, we'll be very happy to do that. Us as a cybersecurity group, we can do that. We can offer our project to create a sort of consortium for the evaluation and benchmarking of blockchain technologies. There is not there isn't a real study on that. We are trying to do very precise study about the security requirements inside a real scenario, because there is a plenty of benchmarking studies of blockchain systems, but there is something is missing there, because they are not simulating Byzantine attackers, they are not simulating real network behaviors, they are measuring inside one single testbed in their laboratory, so they have one machine with 0 latencies and they measure latencies. Oh, it's strange. What we are going to do, we are trying to use a real scenario. That's why the product will be very good. It's promising, and of course we can do like a collaboration on this thing and open like a consortium for the blockchain benchmarking tools.
Is there colleagues from the unit dealing with cybersecurity in Connect in the room, or because we were invited? So, Pederis, perhaps you can help me, but in our new package for cybersecurity, there is this idea to create a certification center in order to ensure that the different products are considered to be good enough from a cybersecurity point of view. Let's imagine that we want to create competencies, maybe not to create a specific center for that, but competencies for those cybersecurity network centers to validate or to stamp one blockchain. Because we have also heard from the previous presentation that the consequence can be very important. The DIO, let's imagine that we are now 5 years ahead. If we have still the DIO and the DIO has been used by millions of European or people in the world, the consequence wouldn't be the same as it was 4 years ago. So at a given stage, we need also to be sure that if we build something on the blockchain, we can make different type of assessment, but there will be a time where we need to be quite confident that
we need to certify the technologies.
We need to certify the technology, and we need also to find other techniques in order to rebuild perhaps a ledger if there is a fork that has to be done, and not to let the world to continue to evolve in parallel. Yeah. So I'm really on demand about good ideas for that, and what is possible, what is not, or how we can start already today some initiative in order to meet this objective. But yes. The question again is for you, but for other people.
Yeah, standardization of certification is a very interesting point, and that there are actually some initiatives, and but right now if I audit a smart contract, all I do is sell my reputation. So there's no official stamp I can put on the certificate that says this has been audited with a certain ISO or whatever in mind, right? As I can do with some other cybersecurity related audits. But there are some initiatives, and I'm personally involved with something called the Cryptocurrency Security Standard, which is an American initiative, and that's fairly limited in scope. It focuses on applications of cryptocurrencies. But it's a start, and that sort of defines a series of conditions an application should fulfill to be considered at a certain level of security, and something like this at European level would certainly be interesting, not just at the application level, at all levels.
Yeah, I mean, building a framework at all levels would be great. It's not easy to focus to all levels in one organization like University of Southampton, working on all levels. But yes, making the force all together and working on this would be very nice. Yeah, I can see some sort of we can build like a certification authority for blockchain systems, blockchain platforms. Through the experimental evaluation of such platforms would be very interesting. Like us as a University of Southampton, we are open to discuss about it, for sure.
Yeah, hi, I'm Jiménez, I work for IBM. I absolutely understand where you're going at in trying to regulate or certificate the applications and protocols and so on, but that would be in direct conflict with establishing your own blockchain platform. How can you be regulated and provide yourself a platform for that? That would be a question to the guys of the Commission.
I'm not sure that I have the answer, that's why I have several questions, but I mean, what we are doing now at the Commission is not to recreate our own technology. I mean, we are going to exploit existing technology, and it will be in first step in a permission environment, but which is open to several, if not almost all the member states and the associated countries. So, which means that we create our mission is to create a kind of trust infrastructure, but which is controlled by almost all the European countries. So the point is that we are not. What we want to achieve is indeed to have a kind of benchmarking approach that will enable us to, when we want to launch an application on this infrastructure, to provide enough guarantee that there will be no cybersecurity issue. I don't know if it answers your question, but I don't see the conflict here about between what we aim to do and to have a cybersecurity approach. At this stage, again, our point is not to develop the new technology, to create ourselves a new consensus, but to be able to test them, maybe to select a few options. And for us, one of the key questions is if we start to build a ledger or several ledgers for supporting application, then if we discover a failure, what will happen, how we can be sure that we'll continue the services. This is something which I think concerns this initiative, but it's also a question that any type of company or consortium would have themselves, I think.
Yes, exactly. The final goal of a benchmark is to offer a service to the clients that are thinking to integrate blockchain in their services, not one that want to develop a blockchain. So if I want to use blockchain, I need to be aware about the technologies around and identify the right technology for my needs. So if I can have less security than performances, I will go for a blockchain. If I want more secure blockchain, I will go for another scenario. How can we evaluate today these things? It's not easy. With a benchmark tool, maybe it would be easier or better, the identification.
Yeah, so I had a question in regards to the certification authority idea. So do you intend to have this approach for the blockchain platforms themselves, and maybe specifically the algorithms different platforms use for the consensus, for example? Or do you also intend to use the certification for specific applications? So do you want to, like, you can have an exchange which is implemented on some platform which can have a certification. Like, take an exchange on Ethereum, for example. Ethereum might be very nice in its consensus layer and get a certification. Would the application on Ethereum inherit this certification, or would you have like an additional certification for the application on top of that?
I don't want to take too much the microphone, because we are looking for different suggestions for that, or recommendation or approach. I mean, I think both are relevant. I mean, in one case, what matters, if we are thinking about providing some services through blockchain, it is the specific context of the application which matters. So in that case, we could imagine that if the application is not too demanding in terms of let's say, performance level or stuff like that, based on this dilemma or trilemma that you have explained, there can be some technical choices that are made in order to be sure that in this specific context there is less issue of cybersecurity resilience. However, if we start to use one technology or family of technology, or if we plan to use different block of technology, in that case, our questions are more general and concern are not limited to the application for sure. So we are interested by both aspects. Again, at this stage, we are in a kind of reflecting mode. I mean, nothing is decided, or there is no European approach decided here, except the general one on cybersecurity. That could inspire also what should be done for the blockchain. And I'm asking also the question because in the context of the future programs that we have in Europe, not only a research innovation program, but also a new program which is called Digital Europe Program, there is a plan to fund those cybersecurity centers, and maybe in some months or years, I mean, part of their work could concern also blockchain.
I mean, for application, I think you should build a prototype starting from the network and consensus layer, because the security issues related to a blockchain platform are inherent from the upper layer to the bottom. So first of all, if you have a technology, you want to evaluate the technology, first focus on these two. Once you have the technology, you can evaluate the application up to build on top of this technology. So the benchmark should first identify the right security technologies from these two layers, then move toward the other layers, because if you resolve the problems here, identifying the performance and security metrics, then you can go through the other layers, because you are still secure here, you're already secure here.
All right, excellent. So thank you very much for all your questions, very interesting questions. And thank you very much for this excellent presentation. We are